higher order Euler-Cauchy equations. Yeah. We just use the same way. Yeah. So the based on the Euler-Cauchy equation. So the format is like this. Yeah. And for the solution, we use the similar assumption. Yeah. So the key assumption is this: y equals x to the m. Yeah. But the m here could be complex number. Okay. So real complex, could be complex number. Yeah. All right. So then the first derivative, second, but we need to take nth derivative, right? Yeah. So then you plug in. So then cancellation. Yeah. Yeah. Because after the factorization, there is x to the m, this term, and we can cancel out. Yeah. All right. So then this is highest degree. So this is the highest degree. Okay. Yeah. And sorry, just a minute. Yeah. Right. Highest degree, because there are m. Yeah. So if you count 0, 0, yeah, m 0, 0, n minus 1, there are n. Yeah. Right? Yeah. So n copies, right? Yeah. So m to the n, right? Highest order or degree. Yeah. So it is a polynomial of degree n. Okay. Polynomial. Yeah. Corresponds to the highest order derivative. Yeah. Nth order derivative. Then our algebraic equation also. Our algebraic equation use degree n. Yeah. So here, when you choose order degree, you should be very careful. Yeah. Last time I talked about that. Yeah. Degree and n. When you use these two words, yeah, you should be very careful. Okay. Yeah. For derivative, this derivative equation. Yeah. So what we say, nth order, ODE, things like that. But this is algebraic equation, right? So polynomial, okay. Polynomial. So it's not ODE. So then the order and the degree, when you use, you should notice the difference. Yeah. All right. So this one, because the highest order m to the n, yeah, and a plus lower, order terms, yeah. But if we use degree, yeah, because this is degree, okay. If we use degree, then we say degree n, okay. Degree, the number degree is n, the same as that. If we use order, yeah, this polynomial, the order of this polynomial, then it becomes n plus 1. That's different. Okay? These two concepts different for polynomial. All right, for polynomial. So that's why, yeah. So when you use these two words, you should be very careful. All right. Case 1, distinct real roots. Yeah. So we assume this degree n polynomial, yeah, by the algebraic. Yeah. Remember last time I talked about the fundamental theorem of algebra. That one, based on that theorem, there are n roots. Yeah. And here, this case, n real roots. Okay, real roots. Yeah. So we separate complex and real roots. So the first case, n real roots. Then the solution is very simple. Okay, yeah. So the solution, x to the certain lambda number. Yeah. There were n different lambda numbers. So we get n different solutions. Yeah. Case number 2, multiple real roots. Yeah. So one root repeated certain number of times. So that's special case. So we just consider that multiple roots. Lambda real root of order n. Yeah, so here you can see it's used order word another time. And there is another name we call the multiplicity. Multiplicity k. Okay, this k also the multiplicity of this root. Yeah. Yeah. Then the k roots, yeah, because corresponding to the multiplicity k, we can write k roots in this way. In this way, yeah, yeah. We can prove it, yeah, yeah. But here, yeah, we do generalization. Yeah, remember, for second order ODE, we have the similar results. So here you can treat as the straightforward generalization from the second order results. Yeah. Third case, simple complex roots. Simple. So that is multiplicity is 1. So what do you mean simple, right? Simple or single, yeah, because sometimes we use single. Yeah. That is multiplicity is 1. Of this root equals 1. Okay? Yeah. Then conjugate pair. Okay? Yeah. Why we can consider conjugate pairs? Because here we assume all these coefficient numbers, little a numbers, all these coefficients, yeah, a, j, yeah. So they must be real coefficients. Otherwise we cannot assume conjugate pair. Okay, yeah. Real coefficients. Yeah. So then we have these two real solutions. Yeah? So they're real solutions. And here, yeah. So I hope you do not get confused because I need to put a parenthesis around. So, yeah. Otherwise, you may treat as cosine x times natural log of x. Then you get confused. Okay? Yeah. Yeah. So omega times natural log x should be inside the parenthesis. Yeah. Then multiple roots. Yeah. Multiple roots, you have multiple pairs. Yeah. So multiple pairs. All right. Yeah. So here I also need to put a parenthesis. Okay. Put a parenthesis. Yeah. This is the first pair. Okay. Yeah. Then you have the second pair. All right. Yeah, because with the multiplicity, you need to multiply that natural log, just like this. Multiplicity, you multiply natural log. Yeah, natural log. But the inside, we need a parenthesis around. Parenthesis around. Yeah. Here, I only do the double roots. Yeah, double case. For triple case and, higher order case, yeah, so you can do the generalization easily. Yeah. All right. So that's this special type ODE. Yeah. All right. So then our last topic of part A, 8.4, Laplace transform on Heaviside function. Yeah. Heaviside function, the special function or unit step function. Yeah. Another commonly used name is the unit step function. Yeah. Unit, 1, its value is 1. Step, okay, like a step. Yeah. So if I draw a graph of this function, yeah. So this function, its graph is very simple, 0. Yeah. So the function value, yeah, usually people use the u function, okay, u of t, u function defined. When t, so t, here I should use the t-axis. Yeah. When the t less than 0, then the u function takes the 0 value, okay, yeah, 0 value. Yeah. Then, after 0, quickly jump to 1, okay, yeah, step function, yeah, and the constant, yeah. So this is the unit step function or Heaviside function. Yeah. And this function is very useful in engineering. Yeah. When we represent some commonly used driving force function. Yeah. So remember the driving force function. Yeah. Yeah. And there are some popular force types. Yeah. So we need to use the Heaviside function. Here you can see with Heaviside function we can represent piecewise functions. Yeah. So with this property, because of this property you can see the piecewise property, right? So you have one piece here, another piece here, right? 2 pieces. Yeah. Okay. So these 2 pieces, so this function is good to for representing piecewise function. Piecewise function. Yeah. For example, we divided the axis into several pieces, right? Yeah. The first piece, one function, okay? Yeah, here. All right. Second piece, another function, right? Yeah. Third piece, another function, okay? Yeah. Yeah. Piecewise functions. Yeah. When our driving force has this special property, yeah, then we can use the Heaviside function or unit step function to represent piecewise functions. Yeah. All right. Yeah. So let's look at the definition. I already talked about. Yeah. So here, but here it add extra a. Yeah. So because the starting point. Yeah. So here this is a u of t. So a equals 0. Yeah. But if a is not a 0, you can see you just need to do a shift. Yeah. Shift to the right. So it is u of t minus a. Here we assume a is a non-negative number. So the unit step function, you've shift its graph 8 units to the right. Yeah. So you get this graph. Yeah. All right. Yeah. And before the vertical line 8, it takes the 0 value. Yeah. Yeah. So then, in that way, yeah, you need to use that shift in that way. So that piecewise function, because you need to do the shift, right? So remember, I drew that piecewise, 3 pieces, okay? Yeah. 3 pieces. Yeah. 1 piece here, second piece here, third piece here. All right. Yeah. So then you need to represent the first piece. Yeah. First piece, actually, you need to do subtraction. Okay. So in order to represent first piece, you need to do subtraction. Yeah. Like u of t minus u of t minus a. You need subtraction so you can get this part. Right? Then for the this part you need another subtraction. Yeah. Subtraction of two Heaviside functions. Then the third piece, yeah, another subtraction type, yeah, like that. Okay? All right. Yeah. Question: why we need to study the Heaviside function or unit step function? Yeah. For solving ODEs with complicated right sides of considerable engineering interest, yeah, such as single waves. Yeah. Single wave. Yeah. So wave. Okay. Yeah. Wave usually, we have, function like that, right? Single wave. Yeah. So you only have this part. Okay. Yeah. Only this part. Then the remaining gone. Okay. So remove the remaining part. Single wave. Discontinuous driving forces. Yeah. Discontinuous. So this is the discontinuous driving force. Periodic input. Yeah. Inputs. Yeah. Yeah. All right. Now let's calculate the Laplace transform based on the definition. Yeah. Yeah. Let's calculate one by one. First, we want to calculate this one. Yeah. Then integral. Yeah. Laplace. So we need to remember this is the kernel part. So we copy that kernel part. Yeah. Then the function itself. Yeah. But here, so when you do, yeah, because this function, remember, this function at the left-hand side of A, it's 0. Okay, 0 at the left-hand side. After A, it becomes 1. All right. So left-hand side. So when t less than or equal to A, greater or equal to 0, this function is 0. Okay? Yeah. Because t minus A less than or equal to 0. Yeah. Then this function is 0. Yeah. Then 0, the integral part 0, it's gone. So then when you start 1, yeah, because at A you get the value 1, so this lower limit should be A, okay, not 0. Yeah. So this formula I copied from the textbook. Yeah. So we should do a correction here. Yeah. From 0 to infinity. Yeah. Then so we can calculate the integral. Yeah. Yeah. At A. Yeah. So the lower limit t at A. Yeah. Then you can calculate the limit at infinity easily. Yeah. All right. Yeah. So the answer is this. Yeah. E to the negative AS over S. Yeah. At A. Yeah. Because at infinity, the limit is 0. It's gone. So you just plug in t equals A. Yeah. And negative, right? So because you have negative sign here, but this t equals A, you use the infinity number minus this, right? Yeah, minus this negative number. Yeah, so it's positive. So here it's positive. Yeah. All right. Yeah, so that's the Laplace transform. Yeah, yeah. Formula. Yeah. All right. Then, so let's look at some other properties. Yeah. So here we want to consider, some other functions, f of t. Yeah. But the f of t equals 0 for all negative t. So here you can see, yeah, match the property of the Heaviside function. Yeah. Yeah. Heaviside function equals 0 for all negative t, right? Yeah. So here, this f function has the similar property, equals 0 for all negative t. Yeah. Then, shift. This is a shift version. Shift translated, shifted. Yeah. So this is the function f of t times u of t. So this function, we shift its graph a units to the right. A units to the right. Yeah. All right. Yeah. So that is the. Here, let's draw graphs. Yeah. Original. Yeah. Suppose f. This f is a 5 times sine of t. Yeah. All right. Then let's compare two different way shifts. All right. The first way, we do not shift the f, yeah, but we shift the u function. Yeah. If you shift the u function 2 units to the right, yeah, f. So you fix the f shape. Yeah. But you started at 2, so you draw a vertical line at 2, t equals 2, and before that it's 0. Okay, before 2 it's 0. After 2, then you take the f function part. Okay, like that. So that's the meaning of this function. Then another way shift, but this time you also shift f t minus 2. Yeah. Then you can see the shape of f. Yeah. The whole part you shift 2 units to the right. Yeah. 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 So here just let you get used to the shifting operation. Yeah. Because for this part, yeah, after we introduce the Heaviside function, so you need to do a lot of shift operations. Yeah. So you need to get used to, yeah, shift operations. Yeah. Yeah. Because it's very easy to get confused. Yeah. Yeah. All right. Then second shifting theorem. Remember, we have first shifting theorem. Yeah. So we learned in module 2. We learned the first shifting theorem. Now, the second shifting theorem. Yeah. So I will copy the first shifting theorem here so you can do the comparison. What's the difference of these two shifting theorems? Let's look at the theorem first. Yeah. So this is the theorem. Yeah. All right. So let's read carefully. If little f of t has the transform capital F of t, yeah, then the shifted function, so here we consider a shifted function, f tilde. The definition is this. Yeah. So previous slide, we understand the meaning of this. Yeah. Specifically, when t less than a, yeah, when t less than a, it's 0. When t greater than a, that's the f function with shifting version. Yeah, yeah, with shift version. Yeah. And here you can see this f tilde function. In this definition here, we do not know the value of this function at t equals a, right? So see the definition. T equals a. What's the value of it? What's the value of it? Right? Because we know its value for t less than a. And we also know its value for t greater than. But we don't know its value for t equals a, right? Yeah, yeah. So here, let me explain a little bit. Here, the value at t equals a not important. Okay. Yeah. So the value of this function at this point not important. Yeah. Yeah. So that's why. So even you do not define it, it's not a problem. So why you say not important? Because when you take Laplace transform, we know Laplace transform is an integral operation, right? When you take integral operation, a function at one point, it does not change the integral value, right? Yeah, so here, let me consider the general case. Suppose, let me explain why a function value at one particular point is not important when you consider the integral of this function. Okay? Yeah, when you consider the integral of this function, that value is not important. No. All right. Here, let me draw a general function, f of t. This is a general function, f of t. Now we consider at one special t of a. Yeah. Usually, there is a value here, right? A certain value here. Okay. All right. So now, when we consider the integral of f of t, alpha, beta, whatever, dt, the meaning of this integral is it? We draw two vertical lines, alpha, beta, Then the integral, its geometric meaning is the area, right? The area under the curve. That's the geometric meaning of this integral. All right. Yeah. Now, if you change the value of this point, so you can remove, or you can raise the point to this one. So you can change the value at one point. Then you do not change the area, right? When you take integral, because you want to calculate the area. But you just move one point, it does not change the area. So that's why if you change just one value, single value of this function, the integral is the same value. And here, because our Laplace transform is integral, its Laplace transform is the same thing. So one value missing doesn't matter. Okay? If you want to assign its value, you can assign any value. All right? You can assign 0, you can assign this value, all right? Or you can assign the average of these two values, 1/2 of f of t minus a, also okay. Okay? Because the integral, the Laplace transform, is the same expression. All right. So there are these two formulas. Okay? This is the second shift, because this one is just the inverse. The second one is the inverse of the first one. So the first one, inside Laplace transform, there is a shift operation. For shift operation, you need multiply that u function. U function, shift. Right hand side, you just multiply that e term. That's the second shifting theorem. All right. So this one, you just take the inverse. Take inverse. All right. Then, let me copy the first shifting theorem aside so you can do the comparison. First shifting theorem. Also two formulas. One Laplace transform, one inverse. The Laplace, you can see, the shift appears at the capital F side. And at the little f side, you multiply e to the at function. And here, e to the negative as function, you multiply to the capital F side. And then, at the t side, you do the shift, but you need to multiply that u function. Okay. U shift version. Yeah. So that's the second shift. First, second. Yeah. So you can see the difference. Then inverse. Yeah. Just straightforward way you write the inverse. Yeah. All right. Yeah. Then let me prove why it is correct. Yeah, because the computation is very easy, so we can understand quickly. Yeah. All right. Let's calculate. Yeah. By the definition, capital SF definition, Laplace transform. All right. Yeah. Then we multiply E term in. Yeah. So we, write in this way. Yeah. Then tau plus A, we can use a new variable to represent tau plus A, right? Yeah. For example, t. Okay. T to represent tau plus A. Yeah. Then so t and the tau becomes t minus A. That's a shift. Okay. That's a shift. Yeah. And A is here because when tau equals 0, t equals A. So you should start, t should start from that A number. Yeah. Then here this A, can you write it as this way, and you can change the lower limit to 0? Yeah. You may ask why we want to change the lower limit, because we want to apply the Laplace transform, right? Laplace transform, the definition, the lower limit must be 0. So we want to move this A, lower limit A, to 0. But if you do that, you need to multiply that U function. Yeah. Multiply that U function. Okay? All right. So this one you can see it's the meaning of Laplace transform of F U product with A shift to the right. Yeah. All right. So we prove the formula. Yeah. All right. Next, we can apply these formulas. We want to solve ODE with Heaviside functions. Yeah. Special driving force functions. Yeah. All right. Yeah. Before that, let us practice. Yeah. So let's do a practice. Calculate the inverse Laplace transform to find little ft of capital F is given. Yeah. Tavion, join us. All right. Yeah. The capital F, like this. Okay. 3 terms. Yeah. 3 terms. We just calculate one by one. Okay. Yeah. 3 terms. All right. Yeah. Solution. Yeah. Let's calculate the inverse Laplace transform of the first term. Yeah. But before we do that, we need to use the basic formula. So I copy basic formula number 8. Yeah. And the second formula, number 2. Yeah. These 2 formulas related. Yeah. All right. Then the second shift. This is the second shifting theorem, right? So we also need to use. So we copy these 3 formulas here. Yeah. So let us do. Oh, yeah. So this is the first. Yeah. This is the first shifting theorem, but the inverse version. So yeah. So we get these formulas ready. Then we can do the calculation. Inverse Laplace transform of the, so here you can see the first time, let us ignore this E term, E part. because the E part we will apply the shifting theorem for that. Okay, yeah. So first we consider 1. Yeah. But this formula, sine formula, we need omega at the numerator, so that's why, because we see pi square here, omega square, so we need to add omega number here. So by formula number 8, we get a sine. Yeah. Yeah. After that, then we can divide it by pi both sides, right? Yeah. So the inverse Laplace transform without this E term, so we have it. Okay? Then we add E term back, yeah? Because here we can apply the second shifting theorem. Yeah. We add it back. Okay? Yeah. So when you add it back, then the left hand side, little f function, you need to shift to the a. So what is the a? What? Yeah. So here you see, you multiply the a equals 1, right? Yeah. So negative 1 times s. 1 times s. So a equals 1 here. Okay? Yeah. So then you shift by a. So this is a. T minus a. Okay? T minus a. All right. Yeah? Yeah. All right. So, and u of t minus a. Yeah. So you carefully apply the second shifting theorem. Yeah. So that is for the first term. Second term you can do similarly, right? Yeah. Second term, because you only need to change a. A becomes 2. The remaining the same, so you only change a here. Yeah. So you can write out the inverse Laplace transform of the second term immediately. Yeah. Then the third, then you need to do something different, yeah, because the numerator, the pattern is different. So the second one, we need to use this formula, okay? S square, but we need to change s to s plus 2, another shift, right? Yeah. Plus 2 plus 8, okay? Or, yeah, because this time you need to do shift inside the capital S, F. Yeah. Yeah. All right, yeah, so let's do the third term. Third term, yeah. First, when we start, we take inverse Laplace transform 1 over s squared equals t. Inverse, yeah, so this formula. Yeah. After that, then we need to apply this first shifting theorem. Okay, first shifting theorem. Yeah. With a equals negative 2. So here, a equals negative 2. Yeah, because a, s minus a. So s plus a, 2. Yeah. So e to the at, so e to the negative. Yeah, because a equals a negative 2. Yeah. So e to the negative 2t times this t. Yeah. All right, yeah. So that's the, the part with numerator 1. All right, but after that, you need to add the numerator function back. Numerator function back, when you add it back, you use the second shifting theorem. See? See? Yeah. So you need to, play around, try to get used to, practice. Yeah. Because all these theorems, you need to use them, freely. Yeah. Okay? All right. So then we add that e to the negative 3s to the numerator, yeah, by this theorem. Little f, we know the little f, right? So this is the little f function, okay? Little f function, then when we apply this second shifting theorem, t, we need to replace t by t minus a. Minus a. Here, a equals 3, okay? Yeah, a equals 3. Yeah. So when you apply the theorem, you make sure, yeah, negative, positive, yeah. Sometimes negative, sometimes positive, yeah. So E this time, yeah, a equals 3, yeah, because here e to the negative as, e to the negative 3s, e to the negative as, so a equals 3, not negative 3, okay, not negative 3. So that's why t minus a, this is t minus a, yeah, times, so this part is little f of t minus a, okay, then this part is u of t minus a. Yeah. So that's the third term, inverse Laplace transform, third term. You put them together, okay, you copy all of them together, okay, yeah, all of them together, yeah. So you get, you know, this long expression, okay, yeah, this long expression. Then we can draw the graph, yeah. So this is the graph. But when you draw the graph like this, then can you see, we want to understand why its graph looks like this. Yeah. All right. So here, let's divide this graph into several pieces. Yeah. Piece 1, piece 2, and a piece 3. Okay? Yeah. So 3 pieces. 1, 2, and 3 pieces. All right. Piece 1, only the first term has contribution, right? Piece 1, only the first term has the contribution. Because the second term, third term hasn't started, okay? The first term start from number 1 and to the right. Yeah. The second term start with number 2 and to the right. The third term start from number 3 to the right. Okay? Yeah. So in this first piece, before the second term gets started, so only the first term has the contribution. So you see this part. Okay? All right. Then you move to the second piece. The second piece, two functions, 2 terms has contribution. The first term and the second term, they both have contribution. But why you see nothing here? Yeah, the reason is simple. Because one, you know, the first term make negative contribution. The second term make positive contribution. Adding together, cancel out. Okay? Positive, negative with the same value, so cancel out. Then you only have 0. All right? Yeah. Then, after this number 3, in the third piece, all 3 terms have contribution. Yeah. Yeah, but actually, you will see, because the first term and the second term always cancel out. Yeah, because one take the positive part, the other one takes the negative one with the same value, exactly the same absolute value, but the sign is opposite. One positive, one negative. So after 2, the first term, second term always cancel out. Yeah. Then after 3, only the third term has contribution. Okay, only the third term has contribution. Yeah. 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 The first 2 terms cancel out. Okay. Yeah. So that's the, you know, behavior, understanding of this graph. Okay. Yeah, otherwise, you may feel it is very strange. Yeah. How can you get this kind of graph, right? Yeah. All right. So let us take a 10-minute break.